So in this video, I want to review the sticks and stones problem. And the sticks and stones problem gets its name from, well, a problem just like this. Imagine that we had 8 stones, 1, 2, 3, 4, 5, 6, 7, 8, and our challenge was to put them into 3 piles. And someone asked us, well, how many different ways could you do that? So if I'm going to have 3 piles, I'll make a pile over here. That's pile 1. This is pile 2. Here's pile 3. We could think of a lot of ways of moving my stones around. For example, I could put maybe 2 stones in this pile, maybe another 2 stones in that pile. That would leave me 4 for this pile. That'd be one way to lay out the 8 stones. Or I could put 1 stone over here, and I could put 6 stones over here, and then I just have 1 left for that pile, and so on. There are a lot of different ways to lay out 8 stones into 3 piles, and our math question is, well, how many different ways are there? And you might think, man, I'm not going to very often come up with this challenge. How often in real life am I asked to lay out stones in piles? I hear you, but it's a very useful technique for reasons we'll see in a moment. Let's start by answering the question, though. 8 stones, how many different ways to lay them out into 3 piles? And the insight how to solve a problem like this is really just 2 pieces. First, you have to recognize that, let's say I put a stick here and a stick here. By putting those 2 sticks down, I've now represented 3 piles. So here's pile 1, here's pile 2, here's pile 3. And indeed, if you now allow me to pick up those sticks and move them around, with 2 sticks, I can show you every possible permutation. I could show you every possible pattern of laying out my rocks. I put my 2 sticks there and I got a 2 stones, 4 stones, 2 stones. I could put my sticks somewhere else. Let me take those sticks out and I'll put the sticks elsewhere. I can put the sticks, let's put 1 stick here and 1 stick here. Great, now I have a pile with 1, 2, 3, 4, 5, a pile with 2, and a pile with 1. But by moving 2 sticks around, I can define the 3 piles. That's the first thing we have to realize. We need to place 2 sticks. The second thing we have to realize is that there are some choices where I can put the sticks. I can put a stick there, 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 and so on, basically in between any 2 stones. And so we have 2 sticks that we have to place, and we have 1, 2, 3, 4, 5, 6, 7 places. And of course, the 7 comes from the fact we have 8 stones. There's 7 gaps between them, and the 2 sticks comes from the fact that we have 3 piles. And so with 2 sticks, I have 7 places to put them. Now I can do my math. And the math is actually math. I've got it in the review sheet if you need it, but math you might well be familiar with. If you think of stick 1, there are 7 places you could place stick 1. Any of the 7 is fine. If you think of stick 2, having already placed stick 1, you now have only 6 choices. There are only 6 spots left to put it. 7 times 6 is 42. So there are 42 different combinations of places to put my sticks. And then we have to remember in this instance to divide by 2. And the reason I have to divide by 2 is it doesn't matter whether it's stick 1 or stick 2 in a given position. It's the same to us. And so let me move to a clean screen. The reason we have to divide by 2, if you think of the stone problem, 1, 2, 3, 4, 5, 6, 7, 8. In the math we just did, putting stick 1 here and stick 2 there is one solution that counts. And in the math we just did, 1, 2, 3, 4, 5, 6, 7, 8, it counts as a different solution putting stick 2 there and stick 1 there. Right, because it looked at all the different ways you could put down the 2 sticks. But those are the same to us. Either way, that's showing a first pile of 2 stones, a second pile of 4 stones, and a third pile of 2 stones. And so our math, we got 7 times 6 is 42. Our math double counts. We counted this as if it's twice, as if it's 2 options, and in fact it's only 1 to us. Now, let me do another problem, same spirit, but the more the kind of problems you might see, and a useful thing in real life. So imagine I want to take 3 numbers, I'm going to call them x, y, and z, and they have to add up to 12. And the question is, how many different ways can I do that? How many different 3-number patterns add up to 12? And again, just to make sure we see the same problem, a sample answer might be like 3 plus 5, That's 8. So I'm going to add 4 more to get to 12. That's one possible answer. Another possible answer would be 7 plus 1. That's 8 also, it turns out. So we go add 4 there and so on. Lots of different ways to add up to 12. And the question is, how many different ways, how many different options would we have to do 3 numbers added to 12? And what's cool is we can represent this as a sticks and stones problem. And indeed, almost any other way you think of doing it would be really, really hard to do. But as sticks and stones, it actually comes out pretty easy. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I'm getting good at drawing circles. I have 12 stones. That represents adding up to 12. And again, I'm going to need 2 sticks in this problem. Because if I do a stick there and a stick there, that's in essence showing me the math of 3 plus 5 plus 4, which indeed adds up to 12. And so visualizing it as a stick and stones problem now, we got it, right? We again need to recognize that we're going to need 2 sticks. And again, that comes from the fact that I have 3 numbers. So I need 2 sticks to divide 3 numbers. I have 11 spots. I have 11 places that I can put those sticks. Right, there are 12 stones. There are 11 gaps between them. Just putting my little green dot there so we can visualize them. And then we got it. Again, this is math you might know. If not, it's in the review sheet. So if you think of stick 1, I have 11 places I can put it. If you think of stick 2, there are 10 places left. That gives me 110 options. But we double counted, same logic as last time. We double counted, so we divide by 2. And we say there are 55 different ordered combinations, an X, a Y, and a Z, that would add up to 12. Now, that's the basic setup of the problem, the sticks and stones. We did a couple other things. I want to highlight one more in the video, and then in the handout, there's some other challenges to think about. But one thing you might notice here is I'm only allowing the numbers 1 and up, right? The earliest place I can put a stick is right here, which would set X equal to 1. I could put the stick later over here, would set X to 2, here sets X to 3, and so on. But in this visualization, I forced the numbers to all be greater than 0. It had to be at least 1. But you might have a problem where you don't want to do that. And what's really interesting is we can still use the sticks and stones method just with a small change. So let's try it. Let's try X plus Y plus Z equals 9. Again, I want 3 possibilities, but this time I'd like to consider, for example, the possibility of 0 plus 3 plus 6, and the possibility of 5 plus 0 plus 4, and so on. I want to allow the zeros. Our normal technique doesn't let us do this. Our normal technique forces us to have at least a 1, but no problem. We're going to adjust our technique. What we're going to do is we're going to, instead of solving for X, Y, and Z, we're going to solve for X plus 1, Y plus 1, and Z plus 1. Because now those numbers will be 1, 2, 3, 4, and so on, right? Those numbers will be the kind of numbers I know I can work with. So I reimagine my problem as X plus 1, Y plus 1, Z plus 1. Of course, now my 9 has got to come to a 12, right? Because I just added 3. And so I reimagine the problem as the problem X plus Y plus Z equals 12. And that will give me the answer for this problem. This one solves it as if we can only do the numbers 1, 2, 3, and so on. Fine. And then we'll come back down. And again, just to make sure we're seeing the same thing, when I solve this problem, if it suggests to me the numbers 2, 4, and 6 as the answer, I know that in my real problem, I'm going to subtract 1. So my real answer is 1, 3, 5. And check it out. 5, 3, and 1 adds up to 9. If this problem suggests the answers are 1 and 10 and 1 adds up to 12, I know the real problem answer is 0, 9, 0. Check it out. Adds up to 9. So I take my original problem, I reimagine it by doing the plus 1s, I do the problem I know how to do, and then I can reason backwards to the correct answer. So again, blank screen, let's do it. If I ask you for X plus Y plus Z equals 9, and I ask you to please allow 0 as a possible answer, you say no problem. I'm going to do the problem X plus Y plus Z equals 12. I know to do that problem. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 stones. How many sticks? I guess I can't hear you, but I know you all just yelled out 2 sticks. right? We've been only doing 2 stick problems so far. In the homework, I'm going to ask you to think about 3 stick problems. We're going to do a 2 stick problem for now, though. Great. We have 2 sticks. How many spaces? How many gaps? Answer is going to be 11, right? I have 12 stones, so 11 gaps. And again, I just write it out. It helps me keep track of it. Stick 1 can go in any of 11 places. Stick 2 can go in any of 10 places. That gives me 110. I divide by 2 because my double counting problem. And there are 55 ways to solve our original problem. All right, and in the handout, I have a little bit more teaching of just the logic behind this math in case that's new to you. So I have a little teaching of the logic of that. And in the homework, I'll give you a couple problems to practice this skill, and then I'm going to ask you to think about problems where you need another stick.